I begin with a question, and this will be our theme throughout. So here we let script C denote a collection of curves, and we give a definition. So C admits efficient coverings of measurable subsets of the plane if you give me a measurable set A, subset of the plane, then there always exists a subcollection C prime, so a subcollection of curves, so the A can be covered by this collection. And further, we can do this in an efficient way so that the two-dimensional Lebesgue measure of the error is 0. Okay. So examples you could be keeping in mind to be wondering if the answer is yes or no, maybe collections of all lines or collections of shifts of the unit circle, or maybe the collection of all circles. So keep your favorite examples in mind. So our question is, which collection C admits efficient coverage? Okay. So in this talk, we'll look at some examples and partially answer this question. And we'll also look at some motivation for this question, as well as applications and related results. So sort of an underlying theme here, which is a bit vague, but development of nonlinear projection theory creates interesting geometric results. You'll see many people in this room have seen examples of that. Okay, this is joint work with two postdocs. My postdoc, Alex McDonald, at the Ohio State University, and Alan Chang, who was a postdoc at Princeton at the time of starting to work together, and now he has a job in Washington University in St. Louis, Missouri, United States. Okay. So our question, which collections C admit efficient covering? So I'll keep repeating that throughout. So here are some connections and motivations. This question is connected to the study of Kakaya and Nikodym set, as well as the study of ST Furstenberg sets, which is a very active area of research right now in both linear and nonlinear settings. It's also related to sum and distance sets. So to just give a flavor of why, suppose we're in the situation where C consists of translations of a fixed curve gamma. Then in this case, our covering set will just be translations of gamma, which of course can be written as the sum E, our translation set, plus gamma. Okay. It's also related to the Favard length problem, also known as Buffon's needle problem, and its nonlinear analogs, the Buffon curve problem, as well as projection theories of Marstrand, Besikovich, Falconer sundial. So these classic theorems that relate the dimension or geometric structure of a set to the dimension and measure of the projection of those sets. Okay. Besikovich's theorem in particular says that if you have a rectifiable set, that rather that average projection length can detect rectifiability. Rectifiability is a notion that tells us in some sense how much our object resembles a smooth curve. Okay. It's also related to LP boundedness of operators along curves. So we'll take a look at these things as we go. So now we turn to our first example of a collection that admits efficient covering. You have a guess in mind of what it's going to be. This remarkable theorem of Davies says that lines admit efficient coverings. So you give me your favorite measurable set F with finite measure. Then we can find a set E, which is a union of lines. Maybe I should have called it L, but it's a union of lines, and it covers F, and furthermore, it does so in this efficient way so that the leftover has measure 0. Okay, so this picture is not really complete. We need to we have F is our set we started with, and then we need to keep drawing the pink lines until we completely cover the set. We also notice the angle of these lines is in a sort of tight arc which is a refinement of this theorem. If you look at the proof, you can get the angles in a tight arc. Right. So very nice theorem. So you might ask, can I replace two-dimensional Lebesgue measure with some other measure? Just a deviation. And the answer is yes. So Chornier extends Davies' result to the setting of sigma finite measures. For the purpose of this talk, we will look at Lebesgue measure. Yeah. Let's take a little detour though and point out that it's not possible in general to replace Lebesgue measure by Hausdorff dimension. Okay, so one might ask for variants of this theorem. Variants are, of course, this can replace lines with other sets. Or could I sort of look at a fractal version of this where I replace Lebesgue measure by Hausdorff dimension? And the answer is no. So picture your set F with dimension S. And the question is, can we find a set L consisting of lines so the L covers F and the S-dimensional Hausdorff measure of L is the same as the S-dimensional Hausdorff measure of F. Okay, that might be a little too ambitious. So let's even just make this easier. Let's cross this out and just ask, what if we just require the dimension of L to be the same as F? So we pause here, we poll the audience, and someone says, no, it's definitely not possible, because if you take F to be the unit circle, for instance, that's a one-dimensional set. And whenever you cover this thing by lines, you can eventually convince yourself using Kukeya technology and Schwarzenberg stuff that this line set needs to have dimension 2. So there's a big gap between. Okay. However, there are some reasonable refinements, and this is joint work that I hope I'll have a chance to tell you about another time. Okay. So back to our question, let's look at some examples. And the first, all of these examples are actually just immediate application of Davies' theorem. So immediate applications of the linear setting. So how far can we push the linear theory? So example 1, collections of lines. Okay, we have that. Collection 2, the set of all circles. So not translations of a circle of a fixed radii, but the large collection of all circles. These admit efficient coverings. So the idea is you start off with a set you want to cover, make sure it's away from the origin, push it away, apply a Mobius transformation, cover that by line, and then transform everything back to get a covering by circles. Okay. So the collection of circles admit efficient coverings. And there's this important distinction that this does not say the set of shifts of the unit circle admits efficient coverings. We'll hope to get to this eventually here. All right. Next, the set of parabolas of the form x squared plus ax plus b, where a and b can range over R. Okay, so this example was actually pointed out to us by Kenneth Falconer. Thank you for that. So this is, again, a fairly straightforward consequence of the linear theory. And the point is that this little piece mostly resembles a line. Yeah, this part. So the set of parabolas of this special form admit efficient coverings. So we still have, okay, we pushed the linear theory to get to these two examples. What other collections of curve admit these things? So before considering results, let's give some motivation for this question. Okay, so motivation 1, Kukeya and Nikodym sets. So several important examples in analysis involve subsets of RD which have measure 0, which contain lots of lines. So Kukeya sets contain lines in every direction, or line segments, if you want to work at a compact world. But they have measure 0. While Nikodym sets contain lots of lines in the sense that they contain a line through a punctured line through every single point in the plane. Okay, so a Nikodym set is a set of measure 0 that contains the so-called punctured line through every point in RD. So if L sub x is the line that passes through x, we call that line minus x a punctured line through x. Okay. So I guess this is our picture for a Kukeya set, and this is our picture. Terrible picture for a okay. So Kukeya sets underlie these sets work as important examples, counterexamples in analysis. For instance, Kikaya sets underlie Pfefferman's proof that the disk multiplier is not LP bounded if P is different than 2. So this is our first instance of using these sorts of sets and this technology to examine LP to LP mapping properties. And Nikodym sets were used to address an important, very basic integration question of boson. Okay, just some examples. Kikaya conjecture, respectively, Nikodym conjecture asserts that every Kikaya set has dimension n. So this is known for n equals 2 and open for n greater or equal to 3, although there's been some evidence, at least in 3 dimensions, to show it might not be true. This is by Josh Dahl. So you find something that's very Kikaya-like that has dimension in 3 dimensions that has dimension a little bit less than 3. So Tao demonstrates that Nikodym sets generate Kikaya sets. So in this way, Kikaya conjecture implies the Nikodym conjecture. In fact, the well-known restriction conjecture from harmonic analysis implies Kikaya conjecture, which implies the Nikodym conjecture. And so this is very cute, nice. So there's this map, and this map moves or takes lines that go through a given point to a collection of parallel lines. So as soon as you have this beautiful map, then you can take a Nikodym set and create a Kikaya set. Okay. And you just have to make sure that the resulting set still has measure 0. You can do. Kikaya sets fit into the larger framework, as we pointed out, of St. Furstenberg sets. So I won't say too much here. I'll just say that here we can think of this as almost a fractal version of Kikaya sets, where instead of taking a full line, or instead of taking all lines in all directions, lines in all directions, we're just going to take maybe fractal subsets of the lines and guarantee that each line has enough points. And then we have a designated range of angles for our lines. Given one of these sets, the basic question is how large is the resulting object? Okay, and there are lots of names here of people who have contributed to this problem, to the study of these objects, as well as the investigation of nonlinear variants of these sets, where lines are replaced by sets of curves. Okay. Nonlinear analogs of Davies and Nikodym's results, if you look under the hood of these sorts of sets, the constructions of these things, you can use the technology there to produce Kikaya sets. Well, we already saw, here's one way, yeah? So if we want to use this map, though, unfortunately, if this map is very nice and then it sends lines to lines, but if we want to send curves, curves may get distorted under this map. Okay, so our takeaway message then is that the investigation of this question of efficient covering by classes of curves is related to these important questions in harmonic analysis and geometric metric theory. Okay, so let's look a little bit under the hood. How are Kikaya sets constructed? They're constructed using parent trees. So let's just look at this triangle and look at this dotted line. So this dotted line sweeps out, we move it, it sweeps out a little arc of angles here, right? And it does so within this triangle, which has area 1, let's say. Okay, so then I subdivide my base and I rearrange my triangles, and I see I can still sweep out. So if I took this horizontal line and I moved it over here, I still sweep out the same amount of directions, but I'm doing so in a smaller area. So at each stage of the construction, we reduce the area while maintaining the set of directions. Okay? So in this way, you keep iterating this process, and you get this resulting thing that has many directions, arc full of directions with 0 mass. Okay, and then you can just take account of the union of locations of this thing and create your set. Davies' efficient covering theorem, if you look at the original proof, utilizes a similar construction. So let's pretend like this is your favorite set we wanted to cover. Yeah, just like the little points here, the red dots, they all live here. And we want to cover it by lines efficiently. So you want to find an efficient covering by line. So what he does is he looks at these taller and taller and skinnier rectangles where all the mass is concentrating here. Whereas if you look at slices up here, the mass is getting smaller and smaller. The one-dimensional, the big measure is getting smaller and smaller and smaller, and they're beating each other. You have the right thing happening. The problem, though, if we want to say adapt this to efficient coverings by shifts of, say, the unit circle, let's say we didn't think too hard, we just went, we read David's theorem, we're going to adapt it, feeling good about ourselves. Unfortunately, our circles start to get, we're going to replace circles by annuli, and the radii, as the rectangles get taller and taller, the radii are getting larger and larger, and unfortunately, this technique does not seem to work. So we need a different way to obtain efficient covering results for curves. Okay, so we move to our next connection, which is sum and distance sets. Okay, so this is very nice work with Kataru Schumann. So we study sum sets of the form A plus gamma here. So this is the Minkowski sum. And here A is a compact subset of RD, and gamma is a sufficiently nice curve. So we need some sort of curvature. So for instance, C2 with non-vanishing curvature will suffice, although one can weaken that a little bit. Yeah. Okay. So among other things, our main goal is to relate the dimension and geometric structure of A to the dimension and measure, or even topological properties of A plus gamma. So among other things, we show that if A is a subset of the plane, say, of positive and finite one-dimensional Hausdorff measure, so A is a set of positive and finite lengths. If someone tells you a set of positive and finite lengths, people in this room might think of the four-corner Cantor set, but someone off the street might think of a line. Yeah. Okay. So then A is purely unrectifiable if and only if the two-dimensional Lebesgue measure of A plus gamma is 0. So as an example, if A is the four-corner Cantor set and gamma is the unit circle, then the two-dimensional Lebesgue measure of this sum set is 0. Okay, so this curvature assumption on gamma is quite important, though. So for instance, if instead A were four-corner Cantor set and gamma was a line with this slope equal to arctan of 1/2, then what happens, you end up getting this entire strip that certainly doesn't have 0 measure. So we need this curvature condition where we say the word nice here. Yeah. Okay. So a key idea to proving one is to consider the vertical slices of our sum set and to re-envision those as images under a map, a family of maps. Okay, so let's go ahead and look at this family of mapping. So we're taking our sum set and we're intersecting by these vertical lines. Okay, so here's a point A in orange, and then this thing is a shift of a curve gamma, a shift by A. So gamma is some fixed curve, and we look at this shift. Okay, so then we're gonna, instead of before for orthogonal projections, you have your parameters are the angles. Now our parameters are going to be inside of some interval along the real line. Yeah, so if A is compact, we're gonna let alpha move back and forth across the real line. So let's fix such an alpha and look at this vertical line and slice this, this orange curve. Then we're sending A to its set of y-intercepts along this curve. Okay, so more generally, this is a set function, but in the special case that gamma is a graph and this thing is non-empty, then we're identifying phi alpha sub A with the y-intercepts of this intersection. Okay. So we relate the dimension of A, our set. We'll come back to this. This is why it's highlighted. We relate the dimension of A to the dimension and measure of the image set, which is our sum set, right? Okay, so the sum set is really just encoded by those slices. So this is accomplished by showing that the family of maps behaves very much like the orthogonal map. Okay, so in other words, the family is transversal, okay, which was mentioned this morning and developed by people in this room, including Boris Solomiak, and others. Okay. But in this situation, we don't really need any hard technology. We can just come in and we have basic proofs like Marstrom's and Besikovich's. They go under the hood, we modify the proof, and we say, let's replace orthogonal projections by this family of projections, and then we get a nice toolbox in which to study this problem. Okay. Marstrom's theorem uses nice energy integrals and characterization of Hausdorff dimension in terms of Fourier transform of supported measures, whereas Besikovich's theorem is using this idea of tangents almost nowhere for purely unrectifiable sets. When A is a Cartesian product, we also, as a side note, obtain results on the interior of A plus gamma of pen-distance sets of A, the interior of pen-distance sets, and further of finite point configuration sets over A. So sets of chains and other star-like figures, other graphs over finite graphs over our set A. And this is joint work with my postdoc. Okay, so we can use this similar technology to study all of these geometric problems. So in this talk, we're going to consider a reverse direction. We start with given images and we seek a set that maps to these images. Okay, so before we had A and we want to understand the images, the sum set, the slices of the sum set. Now we have the slices, we have the images, and we want to understand, can we produce a set that gives us those images? Okay, so we come to the prescribed projection theorem. Okay, so Davy's theorem has an equivalent formulation in terms of the prescribed projection theorem. So this is going to give us another proof technique that we can use to explore these efficient coverings. So here we start with our desired shadows or projections, and we aim to find a subset of d-dimensional Euclidean space. We've been working mostly in the plane, whose projections match those choices. Okay, so there's this nice example of Falconer that I guess you can order online even now. One of these things. So the shadow of the digital sundial changes as the sun moves to different projections. So here our projections are the times of day, and we're seeking this set that our dust set, that so when the sun shines through, we get our desired projection. Okay. Did I have, yeah, Falconer on there. Okay, so I'm just stating, you can probably guess what this theorem says, even though it has lots of notation. This is just a prescribed projection theorem written in 2 dimensions. So for simplicity, we state the following in R2, but higher dimensions are available due to Falconer. So here, you start with your collection of projections. So for each theta, you get to choose a theta up to some measurability constraint. Yeah. Then there exists a set E in the plane that gives you those desired projections up to a measure 0 error. Okay, so in particular, the image of this wonderful dust set E covers a theta for almost every theta, and it has the property that the measure of the difference of these two is 0. In other words, the one-dimensional Lebesgue measure of these two pieces is 0. And here, in throughout, pi theta denotes the orthogonal projection. So the theorem says we can construct a set in the plane to have desired projections up to a null set. The equivalent of the prescribed projection theorem and Davy's efficient covering theorem comes down to the point line duality principle, which basically says that if you have these sum sets, you can reframe the slices as projections. So this is an interesting situation. This equivalence is not hard, but it's even easier in the nonlinear setting. So very often the nonlinear setting is trickier. But this equivalence, and I'm going to show you momentarily, this equivalence in the curved setting is actually quite simple. So rather than showing the equivalence here, I'll show it in the nonlinear setting. Okay, so identifies a set of points with a set of lines. So the vertical slices of the union of these lines correspond to distinct orthogonal projections of the point set. Okay. So summary, proving prescribed projection theorems gives an alternative method to proving efficient covering theorems. And that's what we're going to carry that principle through the rest of this talk to answer our efficient covering question. Okay, so let's just take a look to see that prescribed curve projection theorems, defined momentarily, yield, this just says curve, efficient covering theorem. Okay, so start off with a set A in R2. And our goal here is we want to find an efficient covering by, say, translations of some curve gamma. That's our goal. So slice this thing. Let A alpha denote the vertical slice at alpha. And then suppose, the key word is suppose here. Suppose, pretend for a moment that you did have one of these dust set E's that gives the projection that you want. So such, this should say for almost every alpha, the projection of E or the image of E covers A alpha and the error has measure 0. Okay, I guess technically this should be a little bit of abusive notation. A alpha we're thinking of as a slice, so you can think of this as a subset of R, and this is also a subset of R. But visually, we have our set A, we're slicing it, and then we're taking E and we're looking at the image and we're covering that slice. Okay, so I guess this is really alpha comma phi alpha 3. Okay, so suppose you had that, then immediately you're done. That's it. As soon as you have a prescribed projection theorem, you immediately put this together and apply Fubini to say that, okay, well, if I can cover A alpha by this thing, then that means that A is covered by E plus gamma. Because the slices of A are A alpha, and the slices of E plus gamma are exactly these things. And furthermore, in a similar way, the two-dimensional Lebesgue measure of the error is 0. Okay. So this is what we want. We want to cross out the word suppose, and we want to make this T into a capital T. There exists a set E in the plane that acts the way we want for almost every alpha. Okay, so then by proving a nonlinear prescribed projection result, as we just saw, we have to do the work still, but we arrive at the following theorem. So let gamma denote the graph of a C1 function with strictly monotone derivative on compact domain. Okay, so I'll come back to why we need that. So gamma is the graph of a C1 function. For instance, maybe it's the top quarter of the unit circle. Then let A in R2 have finite measures. Then this theorem gives us this blue set E such that A is covered by the sum set and the two-dimensional Lebesgue measure of the error is 0. Okay, we can definitely rephrase this in the language of this is a prescribed projection result. We can just rephrase this. So corollary, the slices of A alpha are contained in the slices of this thing, which are of course just the images of E under the map phi alpha defined before. And the one-dimensional Lebesgue measure of the slices of this thing, so the difference between that projection and the slice of A, has one-dimensional measures. So this says the collection of translates of gamma admit efficient covering. Okay, so some curvature assumption is necessary. We can recycle that same example from before and see that, so A is the four-corner Cantor set and gamma is a fixed line with slope arctan 1/2 to see that this need no longer be true, right? So some sort of curvature is necessary. Okay. And so our curvature assumption is that gamma is the graph of a C1 function with strictly monotone derivative on a compact domain. Okay, and when we look at the proof, we'll see further why we need this assumption. Okay, so as a particular example, the theorem covers the case where gamma is the top half or bottom half, or whatever half you like, of the unit circle. We do not know if it is possible to take the full circle. So the proof is based on obtaining a prescribed projection result for a class of generalized projections, in fact, the one we just looked at before, and relies on a Venetian blind construction. So we'll take a look at that next. So if we want to control the projections, we first need to understand how these projections work. So the fibers for orthogonal projections are lines. We know that all points along, so I'm projecting, say, onto this thing. I know all the points along this line will get projected to the same point. So what are the fibers in our situation? The fibers are just translates of our negative gamma, where gamma is our curve. So if x is an R2, let's call the image of xy. We're interested in the fiber, the inverse image of this. Here's x, we project it, and then we look at its inverse image, which I'm just drawing with this red laser here. So all the points along this invisible line that I'm drawing with the red laser get projected to that same point, or get mapped to that same point, x. Okay. So then we can play around with that, and eventually we'll think, okay, can we somehow just approximate locally here? So we notice that all the points along the tangent, at least close to x, get mapped near this image. Yeah. So let theta alphas of x denote the tangent direction to this fiber at x, which is going to be the same angle as this tangent. Then near x, the projection phi alpha behaves like a linear projection in this direction. Okay, so we're going to have this correspondence between the alphas and these tangent directions. And we want this to be a one-to-one correspondence. So we have that C1 with non-vanishing, with strictly monotone derivative. Okay, so the points along the fiber map to a single point. The points near x on the tangent line map to a small neighborhood of that point. So if I have little points along here, they're going to get mapped to a little interval, whereas if I had taken the normal here, they're going to map to a bigger interval. Okay, so we build the blinds over one of these fibers. So let's see how a basic blind construction works. So let's start off. Remember, we're trying to control the projection. So we start off with one of these little line segments L, and we simply observe that if we project down, nothing happened. We just get a copy of the set. If we project this way, we get a single point. And if we project this way, we'll get what I call median. So a little interval. And we would like to update this situation. I want to replace for median with, say, small. And I want to keep this as unchanged. So this is going to be we're going to have small directions, and we're going to have so-called covering directions. Every parameter needs to be either a small or a covering parameter. Okay, so we take L and we divide it into n equal pieces, and we rotate each one of those pieces. So this is going to be our new set. Throw away L, and now we're going to have this set. So we don't want to ruin the fact, remember, if we projected this way, we had small. We don't want to ruin that. So let's make sure theta naught is small so that we're working in a small neighborhood of L. So you'll no longer have just a single point. Have a little interval as long as we stay close to L. And then now, as long as we've tilted these things, now if we project this way, which was previously medium, it's now also small. Okay. So keeping, again, theta naught small ensures we stay in a small neighborhood of L. And this ensures the projection of the blind construction is still small in the original direction. Okay. And so then we iterate this. So you can picture there's this rectangle, this small rectangle my construction lives in. Then I take each one of these pieces, I can replace them by, or picture little small neighborhoods around them and iterate this construction, divide this, rotate it a little bit, extend. Why do we extend? We extend so that our projection down is unchanged. Right? So you extend each one of those a little bit, and you're living within this small rectangle, so you haven't ruined your smallness in this direction, but you gained smallness in now this direction. We're expanding our small parameters. Yeah. Okay. So this is the update, and these guys stay the same. Okay. So this process can be iterated using small angles of rotation and a large number of steps to produce a set with small projections in a wide range of directions. So this gives us control over our projections, and we can use these things as building blocks to make our dust set. Okay, so at each stage, again, we stay within a small neighborhood of the previous construction so that we're continuing to improve our lives. Okay, so I'm really selling this here. So our proof in the nonlinear setting largely deviates from Falconer's, as we cannot rely on affine transformations to increase the complexity of the parameter range. So Falconer has this very clever argument where he runs the Venetian blind construction, and then he replaces each one of his slants as little blind pieces by these horizontal pieces. You can apply this affine transformation, and the whole fruit of applying this affine transformation is expanding the range, the complexity of your small and your covering parameters. So from instead of just being small covering, eventually we want something like small covering small. You know, we have some diversity here. So we can't do that. So we need to come up with some new ideas that are unique to the nonlinear setting. So our fibers are not lines. Further, we need to approximate one of these given fibers by a polygonal path and build blinds over each piece. So we'll build blinds over each one of these pieces, and then we need to be careful that these pieces communicate with each other. So for covering parameters, they help each other. If I cover, you don't have to. For small parameters, they might work against each other, right? So we need to make sure that all the little errors that we introduce, those little epsilon errors when we replace the dot by a neighborhood, replace the line by a rectangle, we need to make sure those errors add up to something small still. Okay. So let's look in the curve setting. In the curve setting, fibers are no longer lines, but are shifts of this negative gamma. So let L be a small line segment here, and let's call V our Venetian blind that we eventually obtain. So each alpha, again, is either a covering parameter or a small parameter. It's going to have one of these labels. So for a covering parameter, we want the image of the blind set to cover the image of L. We don't want to change that property. Okay. So in this case, we need to guarantee that any fiber that intersects L also intersects the blind, which does present a few errors, which we'll get to eventually, but this is what we need to guarantee. And then what does it mean to be a small parameter? If we want the image to be small, so here's the red, we need to make sure these curves, so originally they intersected L and we had a big projection, right? So all of these red lines correspond to inverse images of the projection of L. So now we want to update, we want less points to get mapped to that image of L. So we want to update, now we want these red lines to avoid the blinds. So we need to guarantee the fibers above the points in V typically avoid L. Okay, so that's sort of our goal, right? So if alpha is a small parameter, it corresponds to a small angle theta sub alpha. So as we said, we're going to use this idea that locally these maps C sub alpha behave a lot like orthogonal projections, right? So each alpha gets corresponding, one-to-one corresponding to some theta sub alpha. We cannot have a theta sub alpha corresponding to distinct alpha. So this would be a problem if this was not a one-to-one correspondence. The issue is if we run the risk of having a small angle also corresponding to a covering angle. So if we wanted to improve our theorem and have some object that doesn't have monotone derivative, we run into this sort of error. So that's the limitation of the technique. Because the given parameter can only do a single duty, cannot be a covering direction and a small direction. Okay, so this is avoided by assuming by the hypothesis. So there's a couple of issues that come up. The affine transformation issue comes up. We just have to come up with a solution for that. Another issue that comes up is these curves are finite, right? So these fibers are finite length. So it might happen that we have some covering direction and we look at the inverse image of, say, the image of L, some point in the image of L. So this guy hits L, but he doesn't hit the blind. Okay, so then we go home feeling sad. We think about it for a while and we realize the trick or the way to get around this is to not apply the Venetian blind construction in certain places. So don't do this. Don't apply it if it's not going to hit. We need covering. So blue is covering. Yeah? So blue means it always has to hit the blind. So the trade-off is that we present an error term when we project a small parameter. So yay, we don't do the blind construction, it still hits. But now we've lost the fact that in the small directions, we need small projections. Okay, so we have to somehow balance. We must control how often we don't apply the Venetian blind construction. Okay. So we have postdocs and do lots of small calculations. All right. That's a joke. Okay, so that concludes my discussion of my efficient covering. So I'm just going to look at some related results here. And so I'm going to introduce the Favard length problem. This is a very short, lightning presentation of Favard's problem. So the Favard length is an important property in geometric measure theory. It detects rectifiability. Again, rectifiability is telling us how much our set resembles smooth curves. So we understand linear objects very well. We understand smooth manifolds very well, but then we move into the sort of dust sets, which a lot of us are interested in. So Favard length problem. Favard seeks sharp upper and lower bounds on the rate of decay of the average projection length of, say, case of n, where this is the nth generation in the construction of the four-corner Cantor set, or other self-similar fractal sets, as n increases to infinity. Okay, and so this problem has been studied again by many people, including people in this area. Yeah. And so Favard length is comparable to what's known as the Buffon needle probability, which is the probability that a line dropped at random onto the plane intersects the set, given that we're sticking to it actually dropping on the table. So replacing the line by the unit circle, or more generally by a translated copy of a nice curve, we formulate the Buffon curve problem. So the Buffon circle problem, I think, was originally introduced by, or studied by Nazarov and Bond. So they get nice asymptotic upper bounds for the Buffon circle problem, but the radii of their circle is increasing with n. So it's increasing as the generation increases. Okay, so it'd be really nice to get a result where you have this fixed radii. Indeed, we can do this. So, and we replace the family orthogonal projections again by these wonderful maps, the alpha that we looked at earlier, and we get this so-called Favard curve length, which corresponds, just as in the linear setting, corresponds to the Buffon curve probability, which ends up being the probability that if you drop a circle, translated copy of the unit circle onto your set, subject to constraints that you're staying within the unit square, say, that it intersects. Okay, so our work with Katawi, which we rephrase, says the Favard curve length of the four-corner Cantor set is 0. And so one might ask, well, what's the rate of decay? Okay, and so in several joint works, we obtain upper and lower bounds for the Favard curve length problem, with the best known results in line with the result of Nazarov, Peres, and Volberg. So if this is the Favard curve length, let's denote it by Favard gamma, where gamma is a nice enough curve. Let's say it's the unit circle. And it's defined as the average projection length with these P alpha maps. Then we're interested in this quantity as n goes to infinity. Okay. And we're able to get upper bounds in line with those of Nazarov, Peres, and Volberg. We also get lower bounds. Wrapping up. So this result very much depends on the self-similarity of the four-corner Cantor set. You might ask if you can replace these things more and more general neighborhoods of purely unrectifiable one sets. And the answer is yes. Okay. And so this is joint work with Blair Davey and Laura Kladek, in which we obtain these upper bounds for the Favard curve length in line with Tau's quantitative Bezzecovich theorem. So the idea is you take the Bezzecovich theorem, you quantify each step, you quantify the notion of rectifiability, you quantify the notion of length, and then you go through and you replace orthogonal projections by curve projections and make sure you can still do it. Okay, maybe I'll wrap up there. So there are many goals for future work, just like everyone else. And that's it. Okay, thank you. Yeah. Oh, yes, yes. So beyond translations, can we give a complete description of families which admit efficient coverage? And the second goal got attacked when I put it on the board in advance recently, which I think is a good thing. Yeah, but so it's been refined. It's a work in progress. So the basic idea is, can we come up with some sort of fractal variant of Davy's theorem that might present a sort of reverse of the Furstenberg technology people have been looking at. But yeah, I'm very interested in this. We have these quarter circles. So if you have translations of the quarter circle that admits efficient covering, I would love to understand the full circle.